Hey everyone, today we have Eu Gene Goh on the show with us. He started his work more than 20 years ago with integrated circuit design and is now the Senior Director of Design Engineering at Xilinx. Eu Gene has had so much experience with chip design, and I wanted to bring him on to share about his industry and hopefully inspire a new generation of designers. This will be a two-part podcast. The first part gives us an introduction into the industry and what it takes to get a chip into the market. In the second part, we'll talk about how profound the Tesla D1 chip is for DOJO and also discuss the global chip shortage. If you enjoy the content on this channel, please do subscribe and like the videos. Thank you.
Yeah. Okay, can. So 3, 2, 1. Okay, hi Eu Gene.
Hey, Darcy.
Thanks so much for doing this today. The sun is still in our face. Yeah, but so today thank you so much for talking about whatever that perhaps we can talk about chip design, Tesla DOJO, and why the whole semiconductor industry or even chips. There's so much chip shortage going around, and perhaps you can share with us like what have you been doing? What's your background? Like why are you here? Like why did I choose you to come on board the chat? Yeah.
Okay, sure. So I'm a chip designer,
right?
And I started from school. I did electrical engineering,
right.
And so as a kid, I was always interested in what's going on in computers and all that.
Okay.
Right? And I thought maybe being a chip designer was one way to find out more and learn more about it, and so I've been doing that pretty much all my life. But now the last maybe 10 years or so, I've been more of managing the chip design teams. It's been an interesting journey, right? Because you get to see how the technology has evolved over the years. And yeah, the company I work with, we design most programmable chips.
Okay.
Which is a bit unique in the industry. There are not many players.
Okay.
But the department I manage, we focus mainly on high-speed interfaces, data moving in and out of the chip at high speed. So that happens with most chips. You need some kind of high-speed interface because there's so much data going in and out of chips these days.
Okay. So maybe just to share with the audience, right? So like, what are programmable chips? So what do you mean when a chip is?
Oh, okay. Yeah. So most chips, like for example the CPU, they are what we call software programmable. So you write a software program like a C code, and then the CPU would execute commands. But in the FPGA, which is the kind of chips my company sells, it's hardware programmable. In other words, you can change the function of the chip to whatever you want.
Okay.
So the advantage of that is everything is accelerated in hardware, right? When you do that, of course you still need software to control, but then the hardware, so you can make an FPGA into a CPU if you like, or an AI chip. So many things you can do all sorts of things with it. Okay.
So you mentioned you were in chip design, right? So are there different segments of your industry? So like, if you have to have a brief intro into the entire industry, like chip design is one vertical, and then is there other verticals?
Yeah, so even within chip design, you have what we call analog design, and then digital design. And those typically, it more or less splits into those two. So analog design is when you do more with circuits. So maybe I should backtrack a little bit. So you know how chips, basically what goes in is electricity, right? Current. And so it's always voltage and current, which is what you're controlling.
Okay.
The two main things with electricity.
Right.
With analog design, how high your voltage goes and how much current you push through is variable, right? And with that, you can achieve certain things. So, for example, your Wi-Fi signal, it's an RF circuit that's analog, right? But then digital design is when it's just purely 1 or 0.
Okay.
Right? So most of our chips are digital. Most of what controls the chip.
Okay.
But eventually, at some point, because the real world is analog, you need to get into the analog. So in the chips, we have interfaces we call I/O, input output, right? That means when you want to send data into the chip or going out of the chip, typically it's it's some form of analog signal. So analog designers are mostly involved in that.
Okay.
Right. Yeah, and you had to be able to vary the voltages and currents, and that's where you need that kind of circuit. But then once it gets into the chip, it very quickly converts into digital signals, because that's far easier to manipulate, and when you do computations and all that, it's usually in the digital domain.
Okay.
Yeah.
So let's say, right, Apple recently came out with they've launched their M1 chips,
Yeah.
right? So what's the whole process like? Let's just have a brief overview, right? So
Okay.
From start to finish, where has the chip went, and what has gone into the chip,
Okay.
such that we have the end product today? Like,
Right.
roughly, what's the process like?
So it typically starts with what we call an architectural specification, right? So usually in a design side, they have system designers that have to figure out, okay, for this chip, because nowadays chips are complex, there's a lot of things in each chip, so that's why they call them system on a chip. So really, literally you have the whole system on a chip. So you have to define that system first, and so you decide, okay, how much CPU power you want in there. Do you want a GPU, a graphics processor? How much memory you need? What are the input-output interfaces you want to have? So those are the most basic things you need to define. Then of course other things like what kind of performance you're trying to hit, what kind of bandwidth, how much data can you push in and out at any one time. So that has to be specified usually in some kind of a documentation, so that down in that whole chain of designers, they can understand, everyone is sort of on the same page what you
Okay.
need to do. So that architect is usually quite important, right?
Okay.
And it may not be one person, it could be a committee.
Okay, so an architect is something like x86 or x64. Is that
Well, that's
considered
architecture.
Architecture.
That's the kind of instruction
Okay.
that CPU executes.
Okay.
So that defines for example, what kind of instructions to a CPU means you format the data in a certain way, and you execute it in a certain way. And different architecture, like you have x86, you have ARM, they have different ways of doing it, but essentially they try to do the same thing. The architect is the person who says, we need how many CPUs or how many cores, and that has to talk to how many GPUs. For example, in an M1 they have both, right? Then they also have things like, okay, in the CPU you may have to define how much cache, how fast it's going to go, what's the clock speed. When they talk about how many gigahertz, right? When they talk about chips that's actually telling you how fast the chip is running at, the clock in the chip, and that defines how much data or how many instructions it can process at any one time. And then the memory is important, because a lot of times when you're executing the code, you need to temporarily store information on the chip, because it's faster to retrieve that, right? So in the case of the M1, they have, of course, all CPUs have caches, right? That's for temporary storage, but then they also have storage like RAM. So in a CPU you have RAM, right? Random access memory. And in the M1, for example, the RAM is on chip. It's on the same package in a different die, and that's one of the reasons it's so efficient. So those are decisions that they make on the architectural level.
Okay.
And then from there, they have to figure out, okay, then how do we do this to achieve the aims that the architect has said that they want to meet. Yeah.
Okay. So after the architecture, then what's next?
Okay, so after that, then it gets translated in something called a microarchitecture.
Okay.
Which is then you have to write another document, typically, on how the individual different blocks, so sub-blocks, right? How they work and how they talk to each other.
Okay.
So microarchitecture really boils down to on an execution level, like what sort of sub-blocks you need to have, how they talk to each other. Perhaps it may come down to how much logic needs to be in there as well. Because the higher architecture may say certain things like, okay, you need to have this amount of throughput through the CPU in this time, or you need to be able to execute these number of commands. But how do you actually do that? And in terms of implementation, that is defined in the microarchitecture. And that microarchitecture document is what tells the designer
Okay.
the code that he has to write to eventually become the chip. So the next level after microarchitecture is something we call RTL, register transfer level, which is a kind of code actually, a bit like C code, but it's actually defining the hardware implementation. So C code is software, right?
Yeah.
But this one is telling the tools to convert it into logic, right? So I don't know if you're familiar with logic gates.
Not yet.
So essentially, the chips are made up of millions of gates, logic gates, right? So these AND gates, OR gates, and they are fundamentally they're switches. They're saying, if my switch is turned this way or turned on or off, where should I direct the current? And then if you put enough of these together, you can achieve some form of logic function, right? Like and function. I don't know if you've heard, if you've learned that in school, right?
Correct.
Like one and one is one, 1 and 0 is 0, that type of thing, right?
Okay.
So if you put enough of those together, you can get a chip, right? Together with things like muxes, where you can divert signals depending on where it's coming from.
Okay.
Things like flops, where you have memory elements, where you have you send a bit in and then it's held there until the next clock comes and it goes through.
Okay.
So combining all this together, you literally get a logic block, right? And that can do something for you. For example, be a CPU or now from what I mentioned just now about RTL. So that's the code that tells the software tools, this is what I want to do, right? This data, I want to move this data here. I want to do this computation. You can you can write, say, an adder, a multiplier, all the math functions you can define in RTL. And then the next step is you have a very powerful piece of software called a synthesis tool, and that converts that RTL into logic gates. So from this RTL, it would generate the millions of AND gates, OR gates, muxes, flip-flops, and that then needs to be laid out physically. Again, you use some powerful tools to do that, and eventually that becomes a database that you can send to the fab.
Okay.
Yeah.
So all this, whatever that you just mentioned, falls under. Is it already falling under the chip design?
Yes. So the design phase, I would say, start at somewhere around the microarchitecture. So we have some designers that to do this microarchitecture work, and then we have people called RTL designers, right? So they write the code,
right?
After having good understanding of what a microarchitecture is specifying, and then there's another group of people called verification engineers, and they interpret the same microarchitecture document, and they write code that tests that the RTL it's doing what the microarchitecture says it's supposed to do. So when you have a microarchitecture document, it splits into two.
Okay.
You have RTL guys.
Yeah.
Then you have verification guys.
Okay.
They're not supposed to be looking at each other's work. They only have to they're only supposed to refer to the microarchitecture, but the results need to be the same. So these guys are checking that the RTL is doing what it's doing, and if it isn't, they go back and they'll have to tell the RTL engineer, you're not. I don't think you're doing what the architect is saying. But a discussion could happen. Okay. If it's an interpretation issue, right? Because people could have then maybe the document is not written well enough. They may go back and say, you need to define the document better.
Okay.
And that's how we make sure, in a way, that the design is sound, right? Yeah. Because it can get pretty complicated. Yeah. Right? For big chips.
Yeah.
Yeah. But
yeah, it's not easy to get everything towards like. So how do you keep everyone on track, like in the same direction? Because you have that so many things, and what if you do not know what you're?
Yeah. So very often, you have other people that's part of the team called program managers.
Okay.
So, okay, it's always driven by some schedule, right?
Okay.
So there is, before the project starts, you lay out the milestones you need to meet. Like at this point, we need the RTL to be completed. At this point, the verification needs to be done. And then you look at certain parts, certain milestones, and say, this is where we start the physical design, because that takes time as well, in order that we can get a chip out by a certain date. And if we don't get a chip out by a certain date, we may miss our market window, and our competitor may get a jump on us, or our customer may be unhappy.
Okay.
So can you imagine if, take for example, Sony wants to launch their PlayStation on Christmas of a certain year.
Right.
You have to work backwards how long it takes to do this chip, and it could take a year, maybe 2 years to develop this chip, all the way back to when the architect, which is in fact Sony, decide what they want in this next generation PlayStation. They then talk to, say, in this case, AMD made the chip for them.
Okay.
What they want in this chip, and then all that whole process has to take place.
Okay.
And all during this long, it could be a 2-year thing, right? You have program managers that track that all the milestones are hit. If not, what do they need? Do they need more engineers, more heads to help speed things up? And if things are going a bit off track, pull everybody back, right?
Okay.
Yeah, so there is methodology
Okay.
that we follow.
Right. Okay. So you've got the architecture, then you move to the chip design.
Yep.
So once these two processes are done, what's next? What's the next step after you finalize?
So there's a physical design, which is a big part, right?
Sure.
Because you have all these logic gates that has been synthesized from your tool, and then you need to place them so there's another tool called a place and route tool, right? Which is you put all these gates together, right, in as tight an area as possible, and then you need to connect them all up. So you're talking about billions of connections in a typical system on chip today, and that's not an easy task as well, right? Because there's a lot of factors that you need to include in that. Like, for example, timing. How does it, you want to run at a certain speed, 2 gigahertz or something, that's not trivial in terms of because the more logic you pack, typically you run more slowly, but then you're trying to push the performance. So there are things that you need to do to optimize that part of the design. But once you're happy with that, then you need to do all sorts of checks again to make sure that the connections are all correct, and there are tools to do that. We use a lot of computer tools to help us, and then there's one more round of verification to make sure that that's also matching what the RTL saying it's supposed to do. Then finally, when all that's satisfied, you can then send it to the fab, and typically we call that a tape out.
A tape out.
Yeah, and it's really funny because tape.
Yeah.
The reason why the word tape is in that name is because in the past, before the days of the internet and all that, they literally used to copy the database into these tapes, as in not even disc tape, right? In the past, magnetic tape used to be what was the storage that we used to pass around, right? But because it's such a big database, only these tape drives could store them, and we literally then pass these tapes to the fab. Okay. Yeah.
Okay. So the fabs are the manufacturing plants that will produce the chips.
Yeah. Okay, there's one more step.
Okay.
So before the fab, it goes to something called a mask generator. So you know how chips are made by layers.
Okay.
Right. So these days chips can have 40, 60 layers depending on the technology.
So one small chip can have
many
40 different layers.
So it's layer upon layer of different materials, right? So at the base layers you may have doped silicon, because it's silicon, right?
Right.
But as you go higher, it typically becomes metal because then you need to do all the connections.
Right.
So you could get up to maybe 16 to 18 layers of metal, and below that you have another maybe 20 odd layers of other things.
Is there a reason why there's so many layers?
Well, it's just part of how it's manufactured.
Okay.
I think the chip technology or silicon technology, it was defined way back that this is kind of the best way to do it. it's part of how the fab needs to, in order to get all this level of integration, the layering method was the way to go because they use lithography, right? Yeah. So how they do it is, that's why they call it a mask, because it's you lay down some material and then you put a mask on it, which is it hides certain areas and it exposes others. Then you shine some light on it, right? Some form of some wavelength of light, and then it causes some of that material to change because of the light, and that's actually eventually what forms the different structures you need to make up all the devices. Devices meaning all the gates,
okay,
right? And it's done by layers, so that's the reason it's been done this way, right? And then the mask, what we call it a mask, is just every layer has its own mask, right? And so that's why chip manufacturing is all done one layer at a time. So you put the mask down, you shine, then you do some processing, right? And then you put the next mask on, and then you shine the light again.
Okay.
And you just keep going.
And all this is in a chip that is probably just a few centimeters by a few cm by a few cm.
But it's done on a big wafer, right? So now they have these 12-inch wafers, are pretty big, and then each wafer may have up to hundreds of chips.
Okay.
So you're doing all that all at the same time.
Yeah.
So you could process, I'm not sure what the throughput is now, right? But you could process many wafers a day, and that gets you thousands of chips.
Okay.
Each time.
And how long is the usual process? Like you just mentioned, like the chip design process, like a few months. How long does it? Or years?
Yeah, it's typically years now, right? From what we were describing from the architecture, it could be up to 3 years, because it really depends on the complexity. And so if you think about Apple coming out with a chip pretty much every year, right? So you have you have a series of. Every iPhone typically has a new chip.
A chip, yeah.
Right. So I don't know exactly how they do it, but they must have multiple teams where they do. One team is working on a particular part of the design process, and another team is working on a different part, and they just leapfrog each other. Right. So maybe they even have 3 teams. I don't know. Maybe if I think about maybe team A, team B.
Yeah.
Team A is in this phase, maybe the physical design phase. Team B was already taped out and now going back to doing the next chip, right? And otherwise, I don't think it's possible to have a chip out every year.
Every year, right?
If you don't do that.
It's quite amazing if you think about it. Like, you don't see such things until you understand how difficult the entire process is.
Yeah, and even now, right? Because, for example, these chips we have in our phones now, 7 nanometer technology, that takes about 3 months through the fab, maybe more. Some take up to 4 months. So Apple is on 5 nanometer now.
Okay.
I don't know. I think that's even longer, right? Because the more layers you have, and now the layers keep building, the longer it takes.
Okay, so when they say 5 or 7 nanometers, right? What does it mean?
Okay, it used to mean the width of the transistor. So it gives an indication of how small the transistor size is.
Okay.
Right? But these days, I think because of some marketing, because it's so competitive between TSMC and Intel and some of the other fabs, it does not accurately represent that anymore. But it still gives people an indication of how small the devices are, and how much integration you can have.
Okay.
There's also this thing about power, because we're also hoping to make chips that burn less power, right? Or not so much burn less power, but do more, burning the same amount of power.
With less. Do more with less.
Do more with less, or the same.
Okay.
Right? So you could have a chip that burns, depending on what applications, like for these phones, right? Maybe the chip cannot burn more than 10 watts of power, or maybe 5. But as we go smaller, we may be able to do more calculations at that power versus a chip maybe 5 years ago, right? More could be, typically with Moore's law, I know you've heard about Moore's law, it should double every year in terms of its processing, and of course there's some costs related to that. The cost is supposed to come down as well. Okay. But it's not been tracking well, right?
Oh, is it?
Yeah, so I think since about 5 or 6 years ago, that the way Moore's law was supposed to work, doubling every 2 years.
Okay.
The chips are supposed to get half the size.
Okay.
And I think half the cost or something. I forget
Okay.
what the exact terminology is, but that's not happening anymore. So it's slowed down, and in fact, some people argue that it's even stopped because we're not getting those levels of integration.
Is there a reason why that you
Yeah.
think that's? What's your opinion on it? Like,
Okay, so my opinion is it's the difficulty of the fabrication now. Right?
Fabrication,
So as you get
okay.
smaller and smaller, there are more challenges now.
Mm.
There are challenges like signal integrity. That means as everything gets smaller, everything gets closer together, and especially the metal connections, they start to interfere with each other. And when that happens, you get all sorts of other effects you need to deal with. So that's one problem.
Okay.
I'm not sure if I'm trying to think what other issues are causing that, but it's actually these kind of physical effects
Okay.
that's making it harder to keep going smaller. And there's a point where I think you can't get the power down more because of there's another problem called leakage, right? Which is how you have this 0 and 1. Typically, there are states where you're not supposed to be burning power if you're, say, at 0 state, right? But that's not possible anymore because the gates have gone so thin and so small that you will continue to get current running across it. Because, ultimately these are made of switches, right? A switch, you turn the switch on, current moves past, you turn it off, the current stops. When the current stops, you're supposed to not be burning power.
Correct.
But then in today's chips, that's not the case anymore, right? Even if you turn it off, there is some what we call leakage current going across. And that accounts for, because if you have billions of these gates now, right? That's a lot of current. And that's another problem that we're facing.
And it's because they are so closely and densely
Everything
packed
is so
together.
small now.
Huh.
You're going to start to get to the atomic scale
Right.
soon, right?
Right.
How small it's going. And that's something else they need to solve.
Okay, so we have the progress has slowed down a bit, and can we say that it's on the manufacturing side of it, like the hardware side, like the challenges is now coming in at the hardware side, or is it?
It's mostly in how to realize these smaller and smaller circuits in a way that meets the expectations.
Okay.
Right, because with Moore's law, we set up some expectation. Right?
Sure.
We want everything to double every 2 years. So that's stopped, essentially stopped now, right? So we're going, the direction is shifted a bit, and that's one of the reasons you're seeing multi-chip wafers now. In other words, it's maybe not the most cost-effective, or effective to put everything on one chip rather. And it's maybe easier to just put 2 chips together, because if you want to squeeze these 2 things into one piece of silicon die, you need to go much smaller.
Yeah.
But going much smaller gives you all these problems. So maybe the way to do it is to have 2. And then find a way for them to talk effectively.
Okay.
So that's the M1 chip is like that. They have one die that's all the processing. Another die is the memory. Right.
Okay.
I'm trying to think of other examples. AMD does that too. So AMD has a die that's all their CPUs.
Okay.
And then another die is all the I/O.
Interesting.
The part that shifts the data in and out. Yeah.
So we're seeing like a mini trend happening where now it's about how efficient you talk.
Yep.
to the
Efficiency.
different- Okay. Okay. So maybe you can share a bit about on the manufacturing process, right? So once you have chip design done, now we move to like the fabs.
Yep.
These are the basically really expensive plants that produce all these chips. So how is it like how do we get like one chip from?
Oh wow.
Yeah. Like roughly, just a rough.
A rough thing would be, so what I mentioned just now, the masking, right?
Yeah.
So it's a bit like that. What happens? It goes to a company that generates these masks. These masks go to the fab. So the fab you have. So you know how the silicon wafer is? It's this long I forget what they call it, right? It's like a tube.
Okay.
And actually they slice this tube up so that you get the wafers, right? Now the wafers are very thin now, right? And now about 12 inches.
Okay.
So this moves through some processing line, and they got all these really expensive machines.
Okay.
Now it's so complicated now because they're using ultraviolet, EUV.
There's this company called ASML that is providing these machines to TS.
In fact, that's one of the bottlenecks is that they can't make these machines fast enough, right?
Huh.
So these are very complex machines.
Yeah.
They do all the different process stages. A lot of it is lithography, which is, like they put a mask, shine the light, and then keep going then until you get all the layers. But then there's also things like when you do metals, the metal lines are so thin now and so small. How do you, they call it deposition, how do you deposit the metal and so that it fits into the traces that you want?
Okay.
And that's the process. So it starts with the base layers, which is mostly silicon and oxide.
Yeah.
Silicon oxide, and then after that followed by the metal layers, which is now mostly copper. Sometimes it's aluminum, depending on which part of it. And then you get this wafer with a blank wafer becomes this thing with all these little chips on it, right?
Yeah.
And you can sometimes you see it in the pictures. It looks like different colors. And then that goes for testing.
Okay.
After that, right? They make sure that each chip is working the way it's supposed to.
Okay.
And some of the times, the design side, we need to come up with the test, what we call test patterns, which is what we feed into the machine that does the testing, that tests the chip on what it's supposed to do, right? So, you know what I said just now about verification?
Yeah.
So the verification people write test benches, which is code that tests the RTL, right?
Okay.
And from there, you can actually also generate what we call vectors, which are basically a huge file of ones and zeros. Because ultimately, that's what the chip does, right? It talks to the world with ones and zeros.
Correct.
So during the testing phase, we're actually feeding in these huge patterns into the chip, a huge library of ones and zeros. And then we observe the chip's output and read those ones and zeros and see if it matches what the verification people were seeing.
Okay.
And that helps us decide if the chip's working or not.
Okay.
Yeah, working the way it's supposed to, whether the manufacturing and there's a whole methodology about what we call coverage. In other words, have you fed in enough ones and zeros to cover all the different functions of the chip? So that you know when the chip spits out its version of the ones and zeros after the processing, after what it's supposed to do, if that matches what it was designed, it's in initial design intent.
Okay.
It's another quite a complicated process.
Okay.
So that's why we, at the manufacturing stage, there's in the fab you have process engineers, right? They control the manufacturing process. Then it goes into these test facilities where we have test engineers and product engineers that test the chip and determine if from the testing, and they also, it's not just normal testing, right? They have to test at all the different temperatures, different voltages, because for example, in your phone, right, when the battery drains down, there will be a time when the voltage drops as well.
Okay.
Right? And when the chip should still work. So the chip needs to work over a range of different voltages, right? That's part of the design, all right?
Okay.
And we have to test that all that works.
Okay.
And then if you're out and about, the temperature is one thing. You go to a cold country, it's something else, right? So the range of temperatures that we check can be quite wide. I think it can be from anywhere from minus 40 Celsius to 125 typically.
How difficult is the manufacturing process like? So even let's just use Apple's M1 chip as an example, right? You have the MacBooks coming in at the 8 cores, the 10 cores, and the M1 Max chip that comes in at 16 cores. So some of them who has taken part, they speculate that your 8 core devices are the one that perhaps are some of the ones that had couldn't be sold as the 10 cores, and then they're being resold as the 8 cores. So how difficult is this whole manufacturing process like? To get it right and to get it perfect, How
Yeah.
difficult? Just how difficult is it?
It is difficult. It's complicated, right?
Okay.
So there are many steps and processes. So exactly what you said just now. A 10-core M1X, is it called M1X, could actually be a 16-core, or rather an 8-core could be a 10-core. They just turn off 2 cores.
2 cores, yeah.
And a lot of times it's because they went through the testing phase
And they realized
and
that.
they realized 2 cores are not working. So there's a way that they can tell the chip, they can program the chip to say, okay, if these 2 cores, if I have more than 2 cores dead, or if I have more than 1 core dead, but I still have 8 cores working,
Yeah.
mark that as an 8-core
8-core
device, and I can still sell it. Yeah, they do that very often.
So it's done very often. What's it called? Sorry.
Binning. Some
Binning.
They call it binning. In other words, the binning is because you have multiple bins,
Yeah.
and then you put the chip into the various bins depending on what your test results are, right?
Okay.
They bin on functionality like that. They also bin on speed. So that's why sometimes you have chips that, I don't know if you've heard of overclocking, right? You know,
Yeah.
people push their
Push
chips,
the chips.
and they sometimes say, well, why is it by this chip I can overclock faster than another? It's because the manufacturing process, there's a spread of when the chips come out. Some chips are faster than others. It's just because of the process is not exact.
Okay.
There will be variations in the thickness of the metal, in the size of there's some variation in the size of the transistors.
Okay, and these are physical limitations.
Physical limitations,
Okay.
and it's the physical limitation of the fidelity of the manufacturing process, how tight you can control it. You can't control it all that tight, so there will always be variations, and therefore the chips that come out would vary in terms of the speed and in fact how much power it burns as well.
Okay.
So then in the testing phase, they would try to sieve out which chips are the fast ones, which are the slow ones, and then they throw it into these different bins.
Okay.
Then they mark it and sell it depending on how they define the product,
Okay.
right? So maybe like you're saying, the 10-core, 8-core, okay,
Yeah.
this one, 2 cores not working, it's sold as
Okay.
8-core, right? And the best ones are the ones that 16 cores are
16
all
cores, all
working, and
working,
you can charge
okay.
more for it.
Yeah.
So that binning process is very important for the chip maker for making money, right? Because they don't waste.
They don't waste,
Yeah, they don't waste. Plus, they can get money from chips that may not
Supposedly
be
not the best.
Not the best.
Yeah.
It's very important.
I can
The
imagine.
GPU people do that too, right?
Okay.
Yeah, that's why from what is one chip, they can make so many different versions of graphics cards because it's just through this binning process.
Okay. So
Yeah.
you may just design one product, but because that one product has imperfections, and then you can create a line of it, which is your entry level, your mid level, and then your
That's
high
right.
end level is what you really intended this chip to be.
And it's because I mentioned just now the mask.
Yeah.
So when you make these masks and you have to make so many layers, right? That mask is very expensive. One time when we tape out, when we talk about taping out, and we make the mask, that cost of that mask could be in tens of millions of dollars. At 7 nanometer, 5 nanometer, it's as much as that. And that's why it's right for designers. It's so important that we don't make mistakes, because if we make a mistake, we may have to change the mask, and that's super expensive, right? And that's the part that we need to be really careful, and therefore they have all this verification and everything
Right.
to check that everything works. Now, because this mask is so expensive, the manufacturer wants to make as few masks as possible. And if they can make more types of chips with one set of masks, you save money, right?
Okay, so a mask is like a mold.
It's like a mold.
It's like a mold.
Yeah,
okay.
it's like a mold.
Okay.
And that's the reason there's this strategy to do binning. With one mask, you can make various products,
Yep.
sort of similar, but you differentiate by speed
Okay.
and performance,
Right.
or turning off, turning on, turning off different things.
Right. Okay. And then so once all this is manufactured, it's
Yeah.
done, then is it ready to be shipped to the client? Or
Once it's tested, packaged, so it still
Okay.
has to go into a package,
Okay.
right? And that has its other complications as well, because nowadays, if you look at the average chip, it's got hundreds of pins, right? So that in itself is another,
yeah.
right? Because everything's so small.
yeah,
Yeah.
you hate it when you damage one of those. And you're like,
The link bends and
Yeah,
you
correct.
and you gotta junk the thing.
Yeah.
And these days the chips are so expensive, so it's quite painful to have to throw one away.
But, sorry, when you say expensive, like how expensive is a chip that comes?
I mean, typically, even if you went out and bought a CPU now, right? If you bought one of these AMD or Intel CPUs, you're talking about $300-400.
Yeah,
could be as high as that or more. Right? Some of them now, chips like the one my company makes could be in the thousands. One chip. So we have chips that are.
That's the cost to the end end consumer.
What we sell it for.
Okay, sure.
It depends on what application it's going into
Sure.
and how complex it is and how big the silicon is. But it also depends on the type of chip. So we make chips that are for aerospace.
Sure.
And those are really expensive because you need a lot of redundancy. Because in space you get cosmic rays, right?
Yeah.
And that could flip the logic, and you need to be tolerant to that.
How does it flip? Like why?
Okay, so you have radiation in space. So the radiation in space, we are protected here by our atmosphere, right?
Yeah.
In space, you don't have such protection. So the radiation is enough to and the worst thing about this is that as you get smaller, the chips get smaller, they're more prone to it. Yeah, because it's easier to flip it, right?
Okay.
Photoelectric effect, right? I think it's called. And that means the chips need to be special. So can you imagine anything that goes to space?
Yeah.
Why space exploration is so expensive is because all the electronics have to be tolerant of radiation.
Okay.
Right.
Maybe. Sorry. I'll need you to help me with flipping. So what does flipping mean?
Oh, right. So you know what we talk about ones and zeros.
Sure.
Flipping just literally means if your transistor is supposed to be at a one state, it can go to zero.
Oh.
Right, yeah, it can, right? Because you're just talking about voltage levels and maybe we don't know. The radiation can impact it in many ways. It can cause something else, and then eventually cause this thing to flip. So, but you can imagine in a chip where there are billions of just ones and zeros all the time.
Correct.
All you need is one bit to flip and then you have an
Everything
error.
is gone. Yeah.
Your data is now invalid.
Correct.
So there are ways to guard against that. So one way is to have redundancy. In other words, you have multiple versions of the same data.
Okay.
So if one flips, you check it against the other guy, and then you think, oh, it's wrong. So I need to figure out which one's right.
Okay.
Yeah.
Okay. So what's it like in your day-to-day job? Like, what's your role? What's your role like?
So as a designer, so when I was a designer, it's just on you work by projects.
Sure.
So if you're assigned to a project and then you're given the project's broken down into tasks, right?
Sure.
So depending on the task you've been assigned, it's always one eye on the schedule. Because that's the thing that would
that's a hard.
It is.
You must hit it, is it?
Not all the time, but there are implications if you don't. Right? Because the chip design team could be hundreds of people. It's not just you. And then down the line, there are other people who may be impacted as well if you delay.
Yeah.
So it's one of those things that we try our best not to, slip the schedule. On a day-to-day, it's a lot of the work is about using the tools, because the design tools are quite complicated. They're very powerful, but with anything powerful, there's a lot of learning and you need to understand how to use it properly.
Sure.
So that's why maybe this particular career you're always learning new things.
Sure.
Because you're always learning more, not just about the technology but about the tools as well. And then the amount of information you have to process now, because the chips are getting so complicated, and an average designer is dealing with a lot more data than maybe 10 years ago. Like exponentially more data.
Sure.
The computer helps with that. The fact that computers have gotten faster, the software tools have gotten better, it helps. But then it becomes a case of how do you manage that data and manage the time you need, because the computers take time to process, right? So if I was doing a synthesis run, it could take 3 days, 2 days, depending on how big a block I'm running or how big a design I'm doing. So you need to plan that if I need to have this endpoint, I need to work back how long it takes, how long the computer time is, how long it takes for me to organize the data to give to the computer, and then organize the data that then it spits out for the next step, right? Because everything happens in stages. So a lot of it's planning. I have to plan what I'm doing, what data I'm sending into the computer for processing into the tool, and then what I expect I'm going to get, and then planning the contingencies, like if it's not quite what I'm expecting, what's next? What am I going to go? Am I going to make some changes and then go one more round? This happens a lot in physical design, because if I tell the tool I want it this way, I want the connections to be like this and all that, and it doesn't meet timing, like I can't get my 2 gigahertz speed. I need to be able to then go back and decide what do I need to do to make the speed that I'm trying. And it could be swapping out some gates, upgrading the drive strength, or there's a whole slew of things, knobs you can turn actually, and it's turning the knobs to the point where you find an optimal solution. I don't know if I can think of an analogy for this. I'll try, but it's at the end of the day, from a view, it's like you have a data set that you're gonna process, and out of the process comes another data set that you need to then decide, using maybe the same tool or another tool, if that's what you want. If it's not, you go back and then you turn the knobs to make sure that you eventually get right, and you may have to iterate on this for a while.
And so these tools that you keep mentioning about, who designs them?
Software. So these are like software.
Are they done in-house or
no,
usually
it used to, many years ago, some companies, big companies like IBM and maybe Intel maybe still have their own tools, but most of chip design companies, they buy from, so there are companies like Synopsys, Cadence, and Mentor Graphics. They make these tools, and they're big companies on their own. They're big software companies.
I can imagine.
So think of it as like a Adobe Photoshop, right? That does photos for you, or Premiere that does your videos. These are special tools that design chips. That help you design chips, right?
Interesting. So will there be a situation where these tools become more accessible to, or you don't see a need for it to become accessible?
Unlikely. I'm trying to think.
Can they become better?
Oh yeah, they're improving all the time.
They're improving all the time.
They have to, because as the silicon technology gets smaller and smaller, it gets more complex. And then I was telling you about these effects where the different wires are affecting each other, the metal. You need to analyze that. You need to find ways to fish out those problems. So the tools are super advanced. I mean, in fact, sometimes I'm amazed they're almost they have their own intelligence almost sometimes.
It's quite interesting, right? Because you have the guys who are working on these tools, and these guys may or may not be the people who actually, like, were they from the highly chance were they from the same industry, or
usually
were they
not, because they would be software people.
Interesting.
But the tools themselves have architects that define what the tools need to do, right? And a lot of times they work with the Fabs. So they have to. So for example, the physical design people who make the physical design tools have to work with the Fab really closely, because the Fab tells you what the design rules are. Right, like what the separation of the wire is, how closely you can pack the transistors or the gates, and then the tool needs to respect all these rules and still come out with the solution for you that you want. Right, because ultimately, when you turn all the knobs, you hope for a solution that works for you. The tool's trying to guarantee that. Yeah, it's quite complicated, and there's a close partnership between the tools, the people who make these tools, and the Fab people, the people who make the process.
So it's very interesting, right? So even in recent years, you have people like Blender, who is really redesigning what we used to think of 3D software. So my question is coming from the fact that, okay, what if you did have better tools? And what if the tools radically change the way you could
maybe with AI, right? There's a possibility. In fact, there are cases where people have used AI-driven tools to make chips. In other words, they take the designer out of the equation, more or less.
They're replacing you.
Yeah. You could, but it's not. I don't think that's going to. On a long, okay, they can't make super complicated chips, right? They can make pretty simple stuff now.
Sure.
Although some of these people who made some of these tools claim that what they did was, but I think it's going to be a while.
Okay.
I'm not saying it won't happen. I think it probably will.
Yeah.
But you will still need the humans there to get the optimal solution.
Sure.
You know how we know from your self-driving that AI is smart to some degree, but there are limits to what it can do, right? And at some point, the humans still need to intervene to get. Because the chips are expensive, costly to make. You cannot afford. You're always looking for the most optimal solution, and therefore. Unless AI gets so advanced, which it could, right?
Sure.
But I think it's quite a few years down the road.
Okay.
Water, right?
Yeah, water. So maybe before we move on to Tesla DOJO, what do you think would be the one thing in your industry that radically, is there a chance for a meta level event to happen where something really
shakes it up? Yeah.
Like,
not. I would never rule out anything like that. But I think for that to happen, there needs to be quite a big change in the materials. So currently we're still using silicon, right, and metal, and that's been a proven formula for 40 years now, maybe more. But people have been researching using other, maybe more exotic materials. Heard of gallium arsenide. I mean, that's been used for a while too, right? But it's for very specific things, and it's difficult. These other alternative processes are difficult to control. But the thing I can think of is if someone came out with a radically new material and process to control it, and then manufactures it in a much better way somehow, you get much better integration without the power increases. That would be huge.
When you say control, what do you mean by control?
Because it's now about, when you get very small, remember I was saying about your process is never exact. You will have, some of the metals will drift in terms of the sizing, the transistors as well. It's the tolerances there that make it difficult, right? So the tighter you can control that, the better your process is going to be. And some of these have come to a point where, because of the complexities of the process, it's difficult to control it. Therefore, you cannot go smaller, or there are all these challenges, or then you have all these other issues that you have to deal with. So if you come up with a process or a material that is easier to control and gives you tighter tolerances, then that's a huge boost, right? Now, the other thing that actually will happen more like in the near future is you will start going to use you start to use photonics, use light. And already we are working on, there are people working on integrating photonics, light control silicon together with the normal chip. Right, because what's going to happen? Actually, in fact, I think that's what Tesla's doing too. In the DOJO, likely the signals that go out to all the other parts of that big supercomputer, right, is probably using optical connections because it's faster and has a longer lifespan. So now integrating. We've been using light to communicate for a long time, right? Optical fibers. But that's always been in these big boxes, and it's just a lot of heat generated because you have lasers and all that. But now they're bringing all that into a package, right? So you could have packages that you have a chip, then maybe you have a different chip that has a whole bunch of things that will eventually lead to a light source, right? Or signals that you're generating with light going out. And that's happening. That's already happening, and I think in the next maybe 5 years.
This is the end of part 1 of our conversation. With this, I hope that the first part has given you a good background into the industry. This will set you up nicely for part 2 of this conversation, of which we will talk about how profound the Tesla D1 chip is, what it means for Tesla, and also to dive into the global chip shortage. Thank you and have a great one.